Where's that plating coming from, guys? Yes, from the ions in solution. So let's say the ions in solution were copper 2, and they are blue. Okay, so we have this nice vibrant blue solution, and this whole process is occurring. And what do we see start to form in the cathode? So what do we notice? So hold up. Give me at the cathode, little guy. This is our electrode, and there's copper 2 down here. What do you notice here? It plates, but you see the plate, and you see it's what? So what color is it? Brownish, goldish, brashish, and copper. It's plain copper. Like, it's very obvious it's copper, right? And so then this, which is blue, which has deposited on here as it accepted the 2 electrons that were coming in from the anode, as this goes away, as it forms the plating, what does the solution look like? It becomes more clear. It becomes very dilute in terms of the ion, so it lets less blue. So that's sometimes the indicators of change. And so if it says there was a color change or a diminishing of color at the cathode, that will give you indication like that is depositing there. Therefore, this is the process of this. I don't know. That's good. So we can see that that's actually electrons in the reactants, which we said reactants represented. Electrons in the reactants represented reduction. Okay, reactants reduction. You remember that? This is like January. Yeah.
Can you use Beer's law with that?
Oh, maybe if you could quantify like time 1, time 2, time 3, took a sample out of it, yes, and they could ask you to calculate concentration. But we actually have never done that. But they always try to throw us this curveball. They try to give us things we've never seen. And they're very good at it. So they very well could do that. Innovative thinking. Keep it up, guys. Okay. So cell notation, you guys feel okay with? It's like the lines. So how do you write it? So let's say this was like aluminum. Okay, so what would that cell be? Aluminum, and then aluminum 3 plus, and then what is this? Hold on, what's this double line representing?
The salt bridge.
That's there now, okay, and
And then Cu2 plus.
Cu2 plus and
Later.
okay, Faraday's constant. Where would you find Faraday's constant?
On your reference table.
As your reference on your reference table, 96,500 or 96,500 or 45 units.
Per second.
Coulombs per mole of electron. Where would you find the moles of electrons? From the reactions, half reaction. So what's aluminum doing? Losing 3 moles of electron. What's copper doing? Gaining 2 moles of electron. So we would, of course, balance it with a 6 to give the 2 and 3 respective coefficients. And let's see here. Where would you get volts most of the time? Or what are volts? Coulombs per second. So sorry, no, amps or coulombs per second. Amps or coulombs per second.
Volts,
so
like the reading you get.
Yes, and that reading is a combination of what? How do you get volts? You have to look at the electron potential, or electron reduction potential. E cell.
Oh, that chart that we got.
Yeah, so you'll get, and so what do? How do you get E cell?
It's reduction minus oxidation.
And so reduction minus oxidation basically tells you this is at the cathode, whatever process happening at the cathode versus whatever process is happening at the anode. Do you flip the sign of E given to you in the tables?
No, because it's in the formula.
Yes, it's already subtracted here, so do not flip the sign because they will always give you reduction potentials. Always. That's just how you write it. You're talking about the possibility of reduction happening. And reduction means gain of electrons. And so really, what value of E tells you it's really likely to be reduced? High or low? High. So many times it's going to be like, I don't know, the highest you can go is probably like a +2, +3 volts. And that means you're like, you are going to be reduced. You will take some of these electrons if you're going to kill somebody, okay? You are going to take those electrons. And it's like, no, I don't really want to gain electrons, I would rather lose electrons, so it's going to have an E value that's what? That's low. Maybe even so low it's negative because it surpasses the oxygen standard hydrogen electrode, the SHE, SHE. Do we remember that? It's the 0. Okay, it's like just a relative comparison to everything else. So if this is positive and this is negative, what is this? Okay, and that's indicative of a very good battery that runs. No, it has nothing to do with rate necessarily.
How long?
Without intervention, so
Oh,
spontaneously, and that means a delta G that's negative, and truly we don't want to call it spontaneous. We can avoid that. We're going to call it TDF, thermodynamically favorable. And if you want to write TDF 16 times in your free response papers, I don't care as long as you define it, because that's not a standard term or abbreviation. Like beer, it's not a standard abbreviation for plating. So we have to sometimes define our variables if we decide to do anything. Yeah.
If you define beer, plating, could you write beer like 4 or 5 times?
They would hate you just a little bit of
But
time.
you could.
Do you want them to hate you when you're writing yours?
No, I wouldn't.
Yes, you could. Like I give a dinosaur, I'm like, this means an IE. No. So, but try to use your time wisely. So because sometimes abbreviating like some things saves some time. Yeah.
Dinosaur is the variable in the
Yes.
dinosaur equals.
That was my dinosaur example. So this is a positive E cell. This is a negative delta G. It's thermodynamically favorable. What kind of electrochemical cell is this? Say again, Jacob. Galvanic. And galvanics are the ones that are also told to be or said to be voltaic. Voltaic is coming from Volta, Mr. Volta, Alessandro Volta, who actually designed the cells. What's the purpose of a salt bridge in a galvanic cell?
balance the charge.
To prevent charge buildup, which occurs on the anode and cathode, because what's being allowed to flow? No, not electrons. Ions. Okay, as I'm saying this really like explicitly because then you'll remember me freaking out on you, but you won't remember me going, I know, what's not that. This. So the salt bridge is what's happening between our two cells. Because where do the electrons flow?
Wire.
The external wire way out here, right? That's where electrons flow from anode to cathode. And what's flowing in here? The ions that are just there to help neutralize the charges that were starting to form on the anode and cathode so that they have the ability to continue their process. Because they're not being driven by anything but just chemistry, right? They're not being driven by anything but the likelihood of reduction and the likelihood of oxidation. So there's no battery that's outside pushing the electrons. So they're not going to flow electrons unless the charges allow for it. Okay? Yeah, I'm feeling pretty good about electrochem. Do you remember NEPI? N stands for moles of electrons from that given reaction. F is Faraday's, or from that given half reaction generally, actually. Faraday's constant, and then E is volts from E cell. Is this on your reference table? I think it is. I could be lying. They should have a line in here.
What kind of reference is this provided during the exam?
This one. This reference table you've had all year. Yeah, that's not on there. That is Nernst equation. That's the Nernst equation. And so as you are thinking about, okay, I can either memorize the Nernst equation, which many people do right before the exam, kind of just do a double take. But what that's actually asking for is at equilibrium, or before equilibrium, what can happen to the E value? Because E cell is denoted at what conditions? At not. What are standards? Yeah, 25 degrees Celsius, 1 atmosphere, and solution concentration, 1 molar. So we're assuming that we're putting not there. We're assuming those assumptions are there. But what if we start to change the molarity of our solutions? What's going to happen to E cell? Well, that's the thing. Are we talking about decreasing concentration of a product or a reactant? And that's where Le Chatelier's comes into play. Because the Nernst equation is a quantitative way of doing Le Chatelier's. If you're good with Le Chatelier's and you can explain it with increasing or decreasing solution concentrations and E cell, then you should be okay. So let's talk about this example. my example I think was aluminum solid plus copper 2 yields copper and aluminum. Balance it. Okay, it looks like it's balanced, right? It's balanced in atoms, but not in electrons. Okay, so what does that mean? Do you remember doing your half reactions?
Yeah.
Bringing back, guys. Copper 2 goes to copper. What has to happen?
2 electrons in the
2 electrons. Okay, aluminum goes to aluminum 3 plus. What has to happen?
3 electrons.
Where?
Products.
Products. So what do I need?
Balance with 2.
Balanced by a 3 up here and a 2 down here. So what's up here? 2. What's here? 3. 2. Okay? So now it's balanced because we balance not only mass but also charge. So we would have done our half reactions to do that in the first place. Okay. So I have my balanced chemical equation. I have now said, okay, at 1 molar concentration of this and 1 molar concentration of this, let's say my E cell, I don't know those values off the top of my head, but whichever one's oxidized and reduced, let's say it's 0.15 volts, normal. But now I say, let me change this to be a 3 molar solution. And this is constantly in flux, right? So there is some sort of equilibrium nature to it. It's not at equilibrium yet, so it's a dead battery, but it has the ability to act in like an equilibrium situation. I've increased the concentration of product. What happens? Shifts. So if you increase the concentration of aluminum 3 plus, due to Le Chatelier's principle, it's going to hinder the forward reaction, aka shift left. So we're going to shift left. What does that do to E cell? Well, it may not be negative because negative would be an electrochemical cell. We're still talking galvanic. So just say it would be lower. Okay? Because the way we phrased it before, and I'm pulling back memories, I didn't actually review this before today. Sorry. I'll turn back that later. So if you shift left, it's going to decrease the driving force in the forward direction. And that will be reflected in E cell. So basically, E cell is referring to the process at hand, which is whoever's being reduced compared to whoever's being oxidized. We're looking in the forward direction for those processes. Because if I go reverse, well, that's oxidized and that's reduced. You see why I'm saying the forward reaction is pretty, it's like the perspective we take on, yea or nay. Okay, so when we take on the forward direction as our perspective, this is being oxidized and this is being reduced. So that's how we got this. So when we use our explanation, we try to say forward direction to say that, yeah, I know I'm comparing this as it is, the way it's written. So increasing, or not increasing it, I'm sorry guys, I thought I decreased. No, it did increase. So increasing the concentration of product would cause a misbalance. So Le Chatelier's principle says shift back to the left. If you shift back to the left, you're going to decrease the driving force of the forward reaction, also known as electromotive force, EMF. Do you remember that? So therefore the E cell will decline or decrease. And so what if I had instead put 0.1 here? Say again? Well, talk to me on the shots before you get to the conclusion. So I've reset. Okay, so I reset. They're both back at 1 molar, and now I'm saying reset from beginning. This is 0.1, not 1. Because
we just shift back left
to make more of the copper, right? This is lower than it was, not 1 molar, so it's still the same explanation, but you're recognizing a different ion. Lowering the concentration of copper 2 plus will cause a decrease or cause a shift left, which will decrease the driving force in the forward direction, aka the EMF, which is correlated with the lower E cell. Now, what would be the only way you would increase E cell? Maybe 2 ways. Say again? Increase reactant concentration to above 1 molar, so it'll need to use up those because basically the collisions increase and it'll increase the rate of forward reaction. Or lower this one and it'll be forced to balance out to an equilibrium concentration. So it'll be increased force of forward reaction. Okay, that's decent. I'm going to back off for now. Let's go ahead and do multiple choice related to Big Idea 3, which starts on what page? Multiple choice starts on It's after the FRQ, so it's page 22. So start on 22, don't write and pack it, Alvin. How, Alvin, are you doing?
Yeah.
Thanks, okay. And, then we'll do some of those for your responses, okay? So if you want to ask each other questions, that's fine. Stay really focused with me. I'm trying to get you to do as much in class, so there's little to do at home. Do at home. My viewers at home. Okay, so question 1 asked about just oxidation state. Answer? E as an elephant. Good. Question 2 asked about, gosh, I've none forgotten by, sorry. I didn't forgot. What's it about? Oh yeah, Bronsted acids and bases. How do you remember Bronsted acids and bases? Bronsted acids are bad. What's BEAD mean? Donors of what? Of protons. So bad acids are donors of protons. And so that's a different way of thinking when in redox and oxidation reduction, we're talking about donation or acceptance of electrons. So it's kind of our two-sided brain there. So the answer was to number 8. B, because this is acetate combining with hydronium to make acetic acid and water. Who's the donor? So the hydronium. So who's the Bronsted acid? Hydronium. Who's the Bronsted base? The acetate. Thank you. Good. Number 9, which is asking about something being oxidized. A species. Try to use the word species. Good term. Both oxidized and reduced. E, because you have this peroxide right here. The O is what oxidation state? -1. That's the only time oxygen ever gets a -1 because of the peroxide nature, making oxidation state of 0 and -2. So then we're going to have a difference in oxidation and reduction. Question 21. Answer is D. Now, easiest way to do it. You could probably go harder, go easy, but in terms of how do you approach it? Does anyone want to give me a straightforward, Courtney?
I kind of did like a BDA chart. I set it up that way, but then I just saw like the mole ratios and divided the 1 mole by 3.
Okay.
It's like hard to explain.
It's hard. That's actually.
And then because I did like the mole ratios, then I ended up multiplying it by 5, and then adding that like.
And adding them together.
Yeah.
Can anybody condense some things together, Kurt?
So I saw that there was 1 mole of CO2, and I divided that by 3 because of the mole ratio.
Okay.
And then it's asking for total moles, so there are a total of 6 moles of the reactants, so I multiplied that by 6.
Okay, let's do that, because basically it doesn't differentiate between the reactants, right? So 1 second, Jacob. There's 6 moles of reactants there, right? 1 plus 5. So just put, and for your logic of stoichiometry, just put 6 moles reactants over 3 mole CO2, because it does specify CO2 to show your cancellation of units. 1 times 6 over 3 is 2. That's my most concise way of explaining that one. You could do it in 2 separate steps, or as a single one. Is that what you're going to say? Okay, cool. Just trying to give you some flexible thinking opportunities here. So question 25 is D. Thumbs up. They try to give you math that is approachable and doable in your head. Okay, we have excess HF2. Heck yeah, we already know the limiting reagent. It's going to be the 3 times 10 to the 23rd molecules of H2. So what'd you do? You did this.
It's about half a mole.
And that's half a mole. How do you know that? Because you're using Avogadro's number. 1 mole of H2 over 6.022 times 10 to the 23rd molecules of H2. Okay. And then you did. So give me specifics, please.
2 times 2 moles of HF.
2 moles of HF over
1 mole of H2.
1 mole of H2, and then molar mass of 20 grams for HF. So I do think writing your work down, especially on the AP exam and right now, gives you an opportunity that, because a lot of times it's weird. No one ever has extra time with response, but everybody in my class has extra time with multiple choice. Because you guys are so used to like pumping it out at 1 minute that you get a chance to go back and check. So I made a mistake before, goofing up a mole ratio when I'm going back and checking, like, oh gosh, I've got my work shown, I see my mistake, fix it, done in 2 seconds, versus going to recalculate the whole shebang. So it's there for you to go back and check. It's not there for wasted space. So that's about half a mole times 2, back up to 1 mole times 20, 20. Okay? And that's our process for 25. Next one, who took a long time to balance that? It gets a little bit, you can get distracted. But I started with, does anybody want to say where they started? Go for it, Jacob.
I did lithium first.
Okay, so you put a 2 in front of the lithium bicarbonate.
Yeah, and then I had 2, and then I kind of forget. Oh, no, then I did carbons.
Right, because there's
And
2
then I
in
did
front of the
2.
lithium bicarbonate, so then you put a 2 in front of carbon over here.
Yeah, and then I think I did,
Oxygens.
And then I had to balance it a certain way. Actually, what I did after that is I saw there was 2 hydrogens.
2 on this side, and then
There was 2 and 4, so I just put 2 in front of each there.
and then it was done.
Yeah.
So it's not too bad to do. I just have to truly, there's supposed to be like an oxidation state change balancing, but I think it takes longer to do that than just doing it yourselves. B was the answer there, 2. Okay, hydrate. Somebody want to tell me how they started the hydrate one? Go for it, Kirk.
I found the moles of the sodium sulfate by itself.
How did you do that?
It gave us the molar mass in the grams, and it was 0.001 moles.
So they gave you the grams of it.
Like after it was dehydrated.
Thank you. Okay, so we see this hydrate, 3.22 grams of the hydrate, and then it said it dehydrated it, and what was left over?
1.42.
1.42. I'm keeping it down there so you can't see the answer yet. That's fine. This is the anhydrate. So what's the difference?
There's no water. 1.8.
1.8 grams of water. So yes, the difference is there's no water because we dehydrated out. This is the water. Who did this? Okay, so the difference here is water makes up this much of the mass, whereas the anhydrate, which is just the sodium sulfate guy, makes up this much mass. So they try to give you the math that's easy. So they gave you the molar mass of what? 142?
Mm-hmm.
Okay, so take your 0.142, 142 grams per 1 mole of that, and Kurt, how did you do that in your head?
It's just 1.42 and 142 is just the decimal unit.
Decimal moves over 2 places, so then we take 1, because it's basically the equivalency of 1, and we move the decimal over twice. So I'm not really sure another way to mathematically tell you that, but it's like, not a 10th, it's 100 of that. Okay, so it's 0.01. And then this is our water piece, and so how much does water weigh? 18. Again, the math is easy. 0.18 over 18. 18 over 18 would be 1, move this one back 1, so this is 0.1. So empirical molecular formulas require solar mole ratios between the guys here. So this is sodium sulfate. So what's the difference? What's the relative difference here? Any takers? Come on, guys. 10. The difference is 10. So that basically means I have 10 times more water in my formula than I have sodium sulfate. So truly what we would do is most of the time just take the lowest moles and divide them both. So if you divide this by 0.1 or 0.01, you divide this by 0.01, this is 1. So I have 1 sodium sulfate for every 0.1 over 0.01 is 10. So for every 10 waters. So it should be a hydrate of 10 or a decahydrate. How hard was that one? Relatively easy or hard? Not too bad? Okay. It does require some logic though before you start the math. Okay. Percent by mass. C, answer is C. Any questions on that one? You really just need to, well, I don't know if I have a short approach. I try to give you guys my tips.
Just look at more. Yeah, I know. You can figure it out.
Yeah. I basically said, so chromium weighs 52 grams, and because it was mathematically it was at 100. So chromium weighs 52 grams, right? Oxygen weighs 16, but 16 goes into 48 3 times. So this, every time they publish a mass, it is mass percent. I mean, every time they publish a percent, it's mass percent, not like mole percent. So it happened to be 3 oxygens was what it took to be 48 grams, and that equivalency was actually equal to 100. So it was actually not too bad. Okay, next one, limiting reagent problem. How did you approach it? Courtney, get me started.
So I first converted molarity and volume to moles.
Okay, so you took what was it, 20?
It was 0.02 and then 0.2 molar. Well, yeah, 20 milliliters.
Okay. I'm gonna go millis, so there's no decimal issues. So 20 milliliters times 0.2 molar potassium permanganate.
Yep.
How many millimoles? What's 20 times 0.2? 4. 4 millimoles of potassium permanganate.
Yeah.
Okay? And then it was 50, right,
Yeah, 50 milliliters and 0.1 molar.
of sodium oxalate? What
No,
was
it was C2O4.
Sodium oxalate?
Yeah, so yeah, so
Okay.
INC.
So what's 50 times 0.1?
There's 5.
5 millimoles. Okay. So we have 5 millimoles of oxalate and 4 millimoles of permanganate. How do you figure out who your LR is?
Just divide by the coefficient.
Divide by the coefficients. What's the coefficient for permanganate?
2.
2 is per coefficient of oxalate.
5.
5. So this is 1, this is 2. Who's my LR? The oxalate, because that's our little trick in our head method where we take the division of the coefficient because it basically puts them in the same playing field, and then allows you to see whoever actually is lower will give you the lower product. So then from here we take oxalate's moles, so 5 millimoles, and we're converting it to what? Carbon dioxide, right?
Yeah, so 10.
10
to
over-
5 ratio.
10 over 5. So 5 times 10 over 5 is what? Oh yeah, it is. Is that 2? It's 10, isn't it? So it's 10 millimoles, which is how many moles? 0.01. Okay? There's not, I don't think an easier way to do that. You gotta work it out. But we did it in under a minute. Go us. Okay? Next one, that is not copper. 1 oxide, that is copper. 2 oxide. I didn't finish my math. I think you're still looking at this over here. This is 10 millimoles of CO2 over oxalate. So that's 10 millimoles, which is 0.1 moles, or 0.01 moles. All right, so next one, glucose and solution. So what do you need to do here? Find what? Moles and then? Okay, so here's the question. This isn't really a math question. This is a sig fig question. It's nothing more. So what's 60 divided by 180? 0.3 repeat, right? So it's about a third. So 0.333. What do we stop at? Doesn't matter right now. This needs to be liter, so over 0.25. So 0.3333 over 0.25 gives me something over 1, right? Well, I see a couple of answers over 1. How many sig figs should it have?
4.
Why 4? And everything. 4 sig figs, 4 sig figs, 4 sig figs. It should be 4 sig figs, which is answer C. So don't get confused like, oh gosh, what's 0.33 over 0.25? It's over 1, and so then you look at the answer choices and it's not even a molarity question anymore. Okay? Is that it? Good? Alright, so I know that we have the FRQs. So I'm going to give you guys, I'd like to go over 2 of those at least today. I'm going to give you guys some more time to work. So these are the most important ones I think I need to do in class with you. So keep proceeding through the FRQs and we'll give idea 3. So stay focused. I'm giving you time in class. We work through the FRQs. In about 5 minutes, I'd like to check number 1, so proceed quickly through that if you've not.